Hello everyone. This is application project presentation of Group 9. Our topic is content-based image retrieval. Our team consists of Praveen Kumar Ujjwal, Neville Nazarani, and myself Zareen Khan. The input dataset to this project is 10 gigabytes of data from Amos. The output is in the form of image file names filtered based on colored choice provided by user. The key point about this project is that it makes use of benefit from parallel processing. As you all know, parallel processing is much faster than sequential processing when it comes to repetitive calculation on vast amount of data. Instant processing on 10 GB of data will be lot slower in single node. This project is implemented using Hippy. You are going to find this application very interesting and useful as you can quickly search through large data set for image of your color preference. Now let us look at motivation. Nowadays, there is a lot of increase in demand for digital data everywhere, and images being the top category among the available data. It is difficult to deal with large amount of data. As the available data increases, it becomes crucial to use the artificial tools for various purposes. As you see the graph on the right hand side, it's the timeline on the x-axis and the data usage on the on the y-axis actually. You will realize that how the video, the image and the audio data is increasing. Actually, it's increasing if you see from 1990s to 2010s. And it will keep on increasing as you see in the future coming years. Images are quite important and valuable resources in the digital humanities. Because of images, digital humanity scientists can get a rich playground for their research. What is digital image processing? Digital image processing is basically a computer-based technology that carries out automatic processing, manipulation, and interpretation of visual information. And its importance is continuing to increase in many aspects of our daily life. As well as in wide variety of disciplines and fields in science and technology. Some of the applications of image processing are television, photography, robotics, remote sensing, medical diagnosis being very critical and important one, and there are lots of other industrial inspection applications. There are some other also important applications which are computerized photography, example Photoshop. The other important application is space image processing, example Hubble Space Telescope images, interplanetary probe images. The key application that I think is really the medical and biological image processing. Example, interpretation of X-ray images, blood cellular microscope images. Automatic character recognition like zip code, license plate recognition, and one of the example of automatic character recognition would be actually EasyPass, which can read the license plate. Of course, the fingerprint, face, iris recognition that can be applied to your mobile phone for the fingerprint, one of the common one that we use in our daily lives. Remote sensing, aerial and satellite image interpretations, reconnaissance, industrial applications like product inspection and sorting. My other team member will continue on this project. Thank you very much for your time. I hope you will like our project. Goodbye.
Well, hello everyone. My name is Praveen Kumar Ujjwal and I'll be taking up the design part of our project. Now that Zareen has explained the motivation and basic idea of our project, let's delve into how we went ahead designing our application. There are many researches going on in the field of image processing, and with the advent of Hadoop, one such project that is budding up is HIPPY. HIPPY stands for Hadoop Image Processing Interface and was originally designed as a research project with the following goals in mind: to provide an open, extensible library for image processing, computer vision application in MapReduce framework, store the images efficiently in MapReduce applications, allow for simple filtering for a set of images, present users with an intuitive interface for image-based operation, and hide the details of MapReduce framework. Well, because the MapReduce design itself is very complicated. So it does provide an abstraction behind the processing. HIPPY will set up applications so that they are highly parallelized and balanced so that users don't have to worry about such details. Now, let's see what HIPPY is. HIPPY is an image processing library designed to use with Apache Hadoop, as I explained earlier. It facilitates efficient and high throughput image processing with MapReduce style parallel programs, typically executed on a cluster. We'll be using a 4 machine cluster, 4 EC2 instances. It also provides a solution how to store large collection of images on Hadoop distributed file system and make them available for efficient distributed processing. Now here in the diagram you can see the different processing of our, here in the diagram you can see the different processing that our brain does when we see an image, and we as software engineers try to replicate them as a computer program that our PC can process. So you can see we have got image restoration, image compression, image segmentation, color image processing, and various other processing that our brain basically does. We in our project will work only with color image processing. Okay, so our application and HIPPY's design can be made clear using this diagram. The primary input to a HIPPY program is a HIPPY bundle, HIPPY image bundle. Now when you install HIPPY, the user gets access to a tool called HB import, using which one can create a HIB object containing all the images and metadata from a folder on your machine. We downloaded this image dataset from Amos, as explained earlier. Using HB import, the HIB file once created gets stored in the HDFS input location automatically. Now getting back to this diagram. After we provide the input, there is a step called as culling step that allows filtering of the images in HIB based on variety of user-defined conditions like spatial resolution or criteria related to image metadata like color, size, etc. etc. The images that survive in the culling stage are assigned to individual map tasks in the way that attempts to maximize data locality. The record emitted by the mapper are collected and transmitted to reducer, according to a built-in map and shuffle algorithm. Finally, the user-defined reduce tasks are executed in parallel, and their output is aggregated and written to HDFS. Let's look. Let's talk some more about image-based map reduce. The user only needs to specify Hippie bundle image as an input, and Hippie will take care of parallelizing the task and sending float images to Mapper. Images are distributed such that there is a maximum locality between the Mapper machine and the machine where the images reside. Images are distributed as float images so that user can immediately have access to pixel value for image processing and vision operation. So you can see that Hippie is pretty much a very efficient algorithm for processing the image. Next is the implementation, which Neville will explain. I'll take up the evaluation once you guys understand the implementation of our project. Thank you. Now that implementation part has been taken care of by Neville, let's look into the evaluation. We'll take a look into how our project behaved in case of node failure. We actually looked into the application's behavior in case of name node failure. Basically, when working with Hadoop cluster, if everything is working fine, Hadoop cluster can handle huge amount of data. But in case of name node failure, without any replica standing by, cause the data to become unavailable. We also tried to run 2 redundant name nodes on AWS as a fix for this issue. The second evaluation that we did was scalability, based on scalability. Let's look what scalability actually is. Scalability is the ability for a distributed system to easily expand and contract its resources pool to accommodate heavier or lighter loads or number of inputs. Alternatively, the ease with which the system or component can be modified, added, or removed to accommodate changing loads. It is typically cheaper to add a new node to a system in order to achieve improved performance. Basically, we can measure the system scalability using Amdahl's law. Let's look into this example. Suppose 70% of a program can be sped up if parallelized and run on multiple CPUs instead of one. Here, alpha is a fraction of the calculation and that is sequential, and 1 minus alpha is a fraction that can be parallelized. So maximum speed up that can be achieved using p number of processors is given by this particular law. That is 1 by alpha plus 1 minus, you can see it over here, 1 minus alpha by p. Now suppose we are using 4 processors and then substituting the value, as in 70% of the program is complete and we are using 4 processors, we get the speed as the maximum speed up as 2.105. Instead of using 4 processors, we put in 8 processors and we get a difference of what, 0.4, that is 2.581. So basically we don't see too much difference when using more processing power. So instead, the solution of achieving maximum speed up could be running the program in a parallelized environment. That is, in our case, we are using 4 EC2 instances with Hadoop running, 1 a master node, remaining 3 slave node. That definitely did improve the speed of our program, the processing speed. Well, that's about it for the evaluation part. If you guys have any question, feel free to ask. Thank you.